We are trying to do exactly what the sun does.
We have to build big machines, very expensive machines to carry out our research.
There's no doubt the job turned out to be more difficult than people thought 20, 25 years ago.
35 seconds on the mark, 3, 2, 1, mark.
Fusion is so important to the future of the world.
3, 2, 1, shot.
The only catch is that we don't have it yet.
3, 2, 1, пуск.
In our estimation, for the next century, we need fusion.
It's a bright, sunny morning in Princeton, New Jersey. Rob Goldston leaves his car in the driveway and rides his bike to work. It's his daily quest for fusion energy, a quest to copy the sun.
And what we're trying to do is imitate the fusion process that goes on in the sun, create energy by the same kinds of physics, but within the laboratory.
The laboratory is Princeton's Plasma Physics Lab. It's been home to fusion research since Harry Truman was president. Goldston manages experiments run by the 75 scientists here, trying to see if fusion could be an economical alternative source of energy. The quest for fusion energy has been a long and winding road, much like the concrete corridors leading to Princeton University's fusion test reactor. A lot of fusion veterans walk through here. Goldston's 16 years in fusion science is only a fraction of the collective 2,000 fusion research years that Princeton physicists have logged. This is where science hopes to open the door to a new future where energy is safe, clean, and unlimited. But even approaching that door has taken many years, lots of money, and engineering wizardry, like this huge fusion test reactor.
And there's a sense that it's a much more expensive experiment than we've worked with before, and so we have to be more careful than before. But it's mostly exciting. It's mostly an experience of new physics, new regimes we haven't been to before. So the experiment experiences exhilaration more than feeling a sense of being imposed on by it.
Princeton's TFTR, as it's called, is among the world's largest fusion test reactors. $350 million worth of copper, stainless steel, and cable. 50 years from now, history may remember TFTR as the forerunner of clean, safe, endless energy. But for what may already seem to be an endless era of research, TFTR amounts to one giant physics experiment to which dozens of scientists dedicate their time and their lives.
It's a 1 megaamp shot with 12 megaamps of balanced beam injection.
The control room resembles the Houston Control Center that monitors space shots. There's even a countdown.
1 minute.
But instead of rockets blasting, here, motors whine. The sound of the reactor draining power reserves to fire up atoms and run giant magnets.
It's perfect. Yeah, look. Oh, that's pretty. That's a nice shot. Look at that. That's really quiet.
They're called shots because each one lasts only about 5 seconds. Scientists feel if they can make fusion reactions last longer, we won't have to worry if we run out of coal or oil.
If we do not have this alternative source of energy, we will be in a world situation that would be much worse than where we could be if this energy were available.
The energy available today won't be around tomorrow. The world's growing population, forecast as high as 10 billion next century, will tax our depleting supplies of coal and oil. Today's nuclear power picks up some of the slack, but safety and reliability issues have already stifled the growth of nuclear fission. The answer to tomorrow's growing demand for power may not lie here on Earth. It may come from the basic energy that powers the universe. The sun and the stars. They're the universe's way of making nuclear energy. But unlike today's man-made reactors that split atoms, the sun makes them fuse together. Its immense gravity traps hydrogen atoms until the sun's blazing core blends them into helium. Their fusion unleashes dynamic energy and titanic heat. The same atoms that power the stars are plentiful here on Earth. Our oceans are rich with hydrogen, the most abundant element in the universe. This is how science understands fusion. Each atom of hydrogen is like a tiny planetary system. It rides a balance of a negatively charged electron orbiting around a positively charged nucleus made of a single proton. Water also has another type of hydrogen, deuterium, an isotope that lends itself to controlled fusion research. It's got an electron too, and a nuclear proton as well. But the deuterium nucleus also carries one neutron, a particle with no electrical charge at all. There's no shortage of deuterium. It's found in 1 in every 6,000 molecules of seawater. It's also easy to extract. But more importantly, it only takes a teaspoon of deuterium to equal the energy you get from 100 barrels of oil. A typical fusion reaction would combine deuterium with another hydrogen isotope, tritium. Besides carrying 2 neutrons, tritium is man-made. It's also radioactive. But unlike today's nuclear reactors, where waste stays radioactive for thousands of years, tritium radioactivity would last less than 100 years. Fusing them forms harmless helium and releases massive energy, sending neutrons bursting away. In theory, those flying neutrons would strike a reactor wall that collects heat to drive electric turbines while also regenerating expensive tritium.
The nice thing about fusion is there's less radioactivity, and if you build the thing right, it really has no ability to disperse itself over the countryside.
Imagine a busy train station, one where people hurry no matter how crowded it gets. Now, it's human nature for people to try not to run into each other, but let's just suppose that people kept coming into the station, but nobody could get out. Well, eventually, as the crowd got more dense, there'd be a bigger chance of a collision. Well, it's that concept of density and confinement that science hopes will force hydrogen nuclei to collide, fuse, and release energy.
Laboratories don't have the sun's gravity or size to clamp so much atomic density in place, but there are other ways to increase the chance that atoms will collide and fuse. The method at Princeton's plasma physics lab is higher temperature. 2 years ago, scientists here used super hot beams, raising the reactor temperature to a record 300 million degrees, 6 times hotter than the interior of the sun. Heat makes atoms speed up. When they're hot enough, electrons break away from their nuclei. The resulting atomic swarm creates a plasma. It's a warm plasma that burns in a fluorescent light bulb. When plasma's hotter and denser, nuclei have a better chance to slam together. But the proton's positive charge makes nuclei repel, just like people scurrying in a train station. They also respond to a magnetic field. It takes a strong one to trap nuclei till they collide. That's where Princeton's TFTR comes in. Embedded inside is a donut-like chamber where plasma is made. Surrounding the chamber, 2 sets of powerful magnets. Their grip resists the plasma's struggle to strike the reactor wall and cool, in effect binding protons onto a collision course. But plasma is as hard to confine as it is to see. It's like trying to hold jello with an elastic band. The view from inside the chamber shows carbon bumpers glowing with hot gas, a sign that some burning plasma is leaking away. Solving the plasma confinement problem could solve the fusion mystery. Right now, Princeton scientists have to put in a lot more energy than fusion reactions give back. By 1991, they hope to break even. That means getting as much energy out as they put in. But TFTR is designed only to test the conditions to make fusion. If future reactors work, they'll make plasma ignite, just like a match lights a fire. With enough fusion reactions, the plasma would stay hot by itself, and outside power needed to ignite it could be turned off.
But we haven't yet got the thermal insulation to the point where the fusion power that's generated would be enough to keep the thing going on its own. We still have to put in our own power from outside.
The Austrian-born physicist who runs the Plasma Physics Lab has been researching fusion for over 30 years. Dr. Harold Firth foresees an experimental reactor by 2010. He also knows the old fusion axiom that success is always 20 years away.
But now, scientific success is now 20 years away. You know, it's at hand. What's 20 years away is the proof that this will be economically attractive.
Princeton's Plasma Physics Lab is among several facilities around the world researching magnetic fusion. Now, that's one approach, but it's not the only one. That satellite dish reminds scientists here that they have some competition. It enables Princeton's computers to communicate with another computer more than 3,000 miles away at the Lawrence Livermore National Laboratory near San Francisco. This California computer complex is the nerve center for magnetic fusion research around the world.
Upload PPPL user message.
It looks a little like a coin laundromat. But there's no cleaning here. It's all thinking and some tape changing courtesy a robot that works like a jukebox. Livermore supercomputer is a multi-million-dollar project run by the Department of Energy. It serves plasma research in more than a dozen American universities, as well as fusion labs in Japan, Europe, and the United States. A high-tech pumping system pipes special liquid that keeps super-fast processors cool. But in supercomputing, they're the hottest thing. They enable several fusion researchers to tap in at the same time.
One of those processors over there might be sending data to New Jersey, for instance, and another processor might be sending it to my dicomet across the room here.
Livermore supercomputer is designed to do in moments what a personal computer might take years. It's become the world's first electronic fusion ambassador.
Well, this particular center plays a crucial role in the international development as well as the U.S. development of fusion.
But ironically, most of Livermore's magnetic fusion research no longer exists. A $300 million project using parallel magnets, sometimes called mirror fusion, was shut down because it cost too much to run. But there is other research here that could give magnetic fusion a run for its money.
3, 2, 1, go.
This is NOVA, a $176 million investment, the cornerstone of what's called inertial confinement fusion. And it takes something this big to hit something so small. The bottom tip of that metal arm holds a tiny pellet containing fusion fuel. It's the dead center of a 5-story target chamber that looks more like a giant metal octopus.
When I first started, I walked in here, it was like being in, a space movie or something, but after a while, it becomes second nature. There's a lot of things to think about when you're doing this. This is just one small part of it.
But this one small part plays a big role in fusion research. Laser fusion, in effect, turns pellets into tiny hydrogen bombs. It only takes a microsecond, but slow motion shows how a laser beam makes the pellet shell blast away. That makes the fusion fuel inside heat up and implode, and researchers hope make deuterium and tritium fuel fuse.
All of this with the goal of trying to improve the fusion process with each shot so that we understand better what's going on, for the ultimate goal of trying to get more energy out of this pellet than we put in it with the laser.
This is a scale model of the NOVA laser. The real thing is over 300 feet long, longer than a football field. It's designed to fire a lot of power in less than a blink of an eye. In fact, in a billionth of a second, it drives 200 times the power of all the power plants in the United States.
6, 5, 4, 3, 2, 1, shot.
You could fit NOVA's control room in a corner at Princeton's TFTR.
Yeah, we got it.
Yeah.
But good shot.
But the laser it controls is the biggest and most powerful in the world. It's the 3rd generation of Livermore lasers, each raising hopes that inertial confinement is the way to go.
That requires a certain minimum fuel pellet size which we do not have enough laser energy to compress a pellet that size.
It means you're going to have to build an even bigger laser.
It means it's most likely that we will have to have an even bigger laser than NOVA.
One of our challenges for the next year and a half to 2 years is to refine our concepts for a technical and economic baseline to show us how we can build that laser at what we tend to call an affordable cost.
Reportedly, it was a secret nuclear bomb that told researchers how much power that bigger laser would need. In a 1986 project dubbed Centurion Halite, scientists found the bomb's intense radiation made a fusion pellet's hydrogen fuel ignite. But Livermore has little to say about it. Much of the work here is classified. Even the energy funding comes from a defense pie. They're not just pursuing commercial power here. Laser fusion lets science study the effects of nuclear weapons within the safety of a laboratory.
Beyond that, there's not much detail, I'm afraid, that I can go into in that area.
Livermore and Princeton are going after the same fusion goal in different ways. They call it a friendly rivalry where nobody's ahead.
But scientifically, I'm sure that we view it as some sort of a race and a rivalry, but it's not an intense one.
It's a very good thing that not all the hopes of the future should dangle from a single thread.
These hopes cost lots of money. Next year's magnetic fusion budget totals over $351 million. There's another $164 million for inertial confinement. But those funds are over $100 million less than peak years when the energy crisis gave fusion research funding a boost.
It's very difficult to motivate political figures who are beset with day-to-day problems to think 25, 30 years in the future.
In the near future, the next decade, Princeton plans to build a new machine designed to achieve ignition. But budget cuts mean the Compact Ignition Program, better known as CIT, may have to wait another 2 years.
And the machine after that may be so expensive that one government may not be willing to pay for it, and we may have to have several governments contributing into it, and that really slows down development.
In the fusion community, Steve Dean is a household name. He's a physicist by trade who lives, breathes, and literally drives fusion. A few years ago, he left a job at the Department of Energy, raised private corporate funding, and moved into a nearby Maryland office.
Actually, I'm going to be over at NRL next Tuesday. Are you going to be in the neighborhood of the Plasma Physics Division?
Dean's Fusion Power Associates keeps labs and private industry up to date on fusion research. He's also kept up with a bottom line, whether costly research and expensive reactors will price fusion out of the market.
I think that's a real problem if that turns out to be the case. I personally believe that we can make discoveries and come up with ideas and methods that will be cheaper than what our knowledge allows us to do today.
Dean is not the only one who thinks fusion will take a global commitment. Fusion scientists are now marking more than 30 years of international cooperation. A top emissary of scientific glasnost frequently meets with American scientists in Washington. Eugene Velikov is the Soviet science minister.
Secretary General Gorbachev, in meeting with President, told him exactly he's interested in fusion, and our government is interested, and make a decision to try to make this internationally.
But fusion science is a lot older than 30 years. 7 American presidents have funded it. Those first funds, though, went to study a fusion science that's both secret and explosive. The hydrogen bomb, the deadliest force known to man. Its wild fusion energy that's uncontrolled. Its development after World War II inspired researchers to try to tame it. But back then, plasma physics was virtually an unknown science. That's why a 1951 edition of the New York Times caught science by surprise. In a front-page article, Argentina's President Juan Perón boasted a laboratory breakthrough, claiming an Austrian physicist working near Buenos Aires successfully controlled nuclear fusion. Skeptical scientists later found there was no breakthrough and no fusion energy. But the story would turn a Princeton physicist into one of the fathers of modern fusion research. Dr. Lyman Spitzer started thinking about new ways to control fusion reactions, but he needed a little seclusion to think them through. So he and his wife went on a Colorado ski trip.
So I was all primed to think about magnetic fields, which is a very esoteric subject. And I figured out on the lift that really the magnetic field should be a method of acting at a distance, pushing on a hot plasma and keeping it from striking the walls, where it, of course, would immediately cool.
Spitzer worked out his ideas and got the Atomic Energy Commission interested.
We grew and grew and grew, and now what you see here is a direct result, or at least an outcome, of those of that early project. These coils that you see here, these are carry electric current in this direction, and that produces a magnetic field that goes around this racetrack, as we called it. That, in principle, can hold the plasma in, and if it's hot enough, the hydrogen nuclei will fuse and produce electric power.
Knowing he was copying the energy of the sun and the stars, Spitzer called his device the Stellerator. He used it to mount Project Matterhorn. It was Princeton's first fusion research, and it was cloaked in secrecy. But fusion's first pioneers got disappointing results.
And in fact, if we'd gone right ahead and built a device that was 10 times bigger than this, it would have worked very much the way the present devices are.
Looking back, it's not surprising that the people were disappointed in their early efforts. There was no way they could have succeeded with the knowledge they had at the time.
But from Russia came some early fusion genius. Dr. Andrei Sakharov and his wife Yelena live on the 7th floor of a Moscow apartment. Together, they've braved the Kremlin's muscle to fight for human rights, a fight that's won Sakharov the Nobel Peace Prize.
Я астры посадила.
But Sakharov's science won him worldwide respect. After working on the Soviet hydrogen bomb, Sakharov turned to more peaceful science. In the early 50s, he and Dr. Igor Tamm wrote a theory of magnetic confinement, fathering the concept that inspired modern fusion research.
Did here and did там, but after many fathers.
I have the inner great feeling that when I think that I took part in the beginning of this very essential work.
Sakharov speaks broken English, but speaking in Russian, he told us through an interpreter, the fusion science that grew out of his early theories is making good progress.
This work turned out to be much more difficult and lengthier than it had presented itself to Sergei Tamm and myself in 1950. But the fundamental principal problems have been overcome. The reasons for instability have been explained, and it seems to me that we not only know that the magnetic fusion device is possible, but also the parameters in which magnetic fusion can become a real operating machine.
How do you think fusion might change the world?
I think that controlled fusion reactors will decide problems of energy production which already have other solutions, and therefore I do not think that fusion will change the world. Its purpose does not have that revolutionary character that the other great discoveries of the 20th century have had, when something was being solved for the first time. All the same, I think that practically it will be very important for humanity. I think that large-scale atomic energy production will receive a great deal from controlled fusion. In the first stage, I think that this will take the form of the breeder reactor, controlled fusion reactions to obtain uranium-238 for use in atomic energy production. Of course, this means of atomic energy is founded upon fission, with all of its difficulties and dangers. For this reason, I support the idea of placing all nuclear power underground.
The fusion breeder that Sakharov mentioned is a concept the Russians still study but found too impractical by Western and Japanese science. It was the concept of safety, though, that prompted Sakharov to return to English and remind fusion researchers to never forget.
We have no right to have another Chernobyls.
The man who's given his life to peace feels science must do the same for the atom. That's not a new idea. Hopes resting on the nuclear promise led the world's scientific nations to start sharing knowledge. So the cloak of secrecy surrounding fusion and fission research started to lift.
Just before the opening of the conference, the United States and Great Britain jointly announced the declassification of their thermonuclear research programs. And the United States unveiled its most promising experimental devices, actual operating machines, like Princeton's B-2 Stellerator. These represent the various paths being explored in a quest for a new source of power. Many of these machines were operated throughout the conference. The Princeton exhibit included a model of the university's Stellerator laboratory, devoted entirely to fusion research. Another approach, the racetrack Stellerator, in which the twist in the magnetic field is produced by current flowing through adjacent groups of wires in opposite directions. The Los Alamos Scientific Laboratory showed a number of operating devices, including Scylla, in which the plasma is superheated by compression. All of the machines are still in the experimental stage, but from one of these research channels may come the elusive secret of cheap, plentiful power, a secret which certainly will be unlocked the sooner as a result of international cooperation.
Fusion first worked in secret because governments wondered if nuclear byproducts might help make powerful bombs. They knew that, in theory, a plasma chamber wrapped inside a uranium blanket would lead to a fusion breeder reactor capable of making plutonium, a key ingredient for nuclear weapons.
People were afraid maybe this was some sort of shortcut for making fissionable material for bomb. So by '58 it was clear that building a fusion reactor just had to be one of the toughest ways on Earth to make material clandestinely for bomb. And then it made sense to declassify.
Suddenly, fusion was heard around the world. And at a 1958 Atomic Energy Conference in Geneva, researchers from a host of nations showcased their fusion science.
Soviets were there, the Japanese, Europeans. And it was remarkable, because up until that time, all these programs had been conducted in secret. And when people opened the veils and they showed the other parties what they had done, it was all the same.
But not for long. In the mid-1960s, Russian scientists working in Moscow announced a major fusion achievement. Using Sakharov's theories, the Soviets improved on the donut-like confinement chamber. Researchers at places like Moscow's Kurchatov Institute invited the world to copy their idea, and the world copied away. They even copied the word Tokamak, a Russian acronym that applies to today's most common fusion research device.
The Soviets opened their fusion research doors years before anyone ever heard of glasnost, symbolizing that scientists around the world find it a lot easier to cooperate than their respective nations do. Perhaps it is today's spirit of glasnost that led the Soviets to invite our cameras in for a rare and comprehensive look at fusion research here in the USSR.
Внимание, готовность к импульсу. Даю отсчет. 3, 2, 1, пуск.
This is Russian fusion research at work. The lab looks a lot different than Princeton's TFTR, but the goal is exactly the same.
The ignition of the DT reaction is the most important step in our whole work. We worked 38 years. And if we don't ignite the reaction, the public opinion will be against fusion. 40 years spent it and not ignited the reaction. That is an unluck.
You're watching some of the international spirit to make fusion work. The man standing is Sam Hoken, an American exchange scientist from MIT. He learned fast that it helps to speak Russian here. He also learned from dusty oscilloscopes and obsolete technology. After hearing how Russian science suffers from technical setbacks and shortages, he came to Moscow armed with his own personal computer.
And that's something that all American scientists and all Western scientists know, that when you come to the Soviet Union to do exchange work, bring your own equipment, everything, including a voltage meter, soldering iron, whatever you want, because even if it's here, it's hard to find and things get tough.
But the brain power here is top-notch. Dr. Vyacheslav Strelkov manages Moscow's fusion workhorse, better known as T-10. It's older and a lot smaller than Princeton's TFTR, but it leads the world in a key type of plasma heating technology. Where most other tokamaks use electric heat and so-called neutral beams, T10 uses gyrotrons that generate the same kind of heat you get when you turn on a microwave oven.
It is a generator, so-called gyrotrons. Each unit produces about 200 kilowatts power, and all energy due to the waveguide go to the plasma in order to heat the plasma. On this machine we have a temperature of the plasma about 10 keV electron temperature of the plasma.
And that is in terms of real temperature?
In the real terms, it is about 100 million degrees centigrade.
How come you're still working with an old style kind of experiment?
It is not, because this experiment is rather difficult, and we have many problems, so we continue the experiment on this machine and construct the new one.
It's called T-15. It's the Soviets' first modern generation tokamak experiment. When it's ready, it will look just like Princeton's TFTR. But there are some key differences. The Soviets are building T-15 with a superconducting coil. It will act like a power bank, storing the energy to heat and confine the plasmas, minimizing the power T-15 will have to drain from Moscow's power company.
A real thermonuclear reactor must have only the superconductor coils. It is impossible, practically impossible, to have a thermonuclear reactor with usual magnet.
T-15 is supposed to start in December. That's more than 5 years since Princeton turned on TFTR. The Soviets had hoped T-15 would have been working right now, but it suffers from a 5-year lag that underscores a fundamental complaint, that bureaucratic rivalries and managerial conflicts often slow down Soviet scientific development.
It is not easy, so many difficulties. Not scientific difficulties, technology difficulties, and also difficulty of organization. Manager, maybe. Problem of management.
Another problem, radioactivity. First-generation fusion reactors will burn radioactive tritium. The Soviets say both they and their American counterparts have painful memories that will force them to minimize contamination.
The public opinion now is against radioactivity. We know in the United States and now after Chernobyl in our state that the opinion is that the energetic must be with such low level of radioactivity.
There's plenty of energy and enthusiasm here to make fusion work. The Russians hope T-15 will help them catch up to fusion science around the world.
Russia until now has been pretty much out on its own. And as experiments get bigger, as it looks like a fusion reactor is going to be a big, complicated, expensive thing, at least at the beginning, it is clear that international cooperation is necessary.
It is nonsense to make a competition in such field as fusion, because it is a very long-term goal, and we benefit from the development of Tokamak in the United States.
The Soviets' appeal for joint fusion development historically gets a lukewarm response at the Pentagon and on Capitol Hill. It's a concern that the Russians are subtly trying to grab Western technology. As one House staff member put it, we don't want to give away the store. Among those concerned, the New Jersey congressman who chairs a House Science and Technology Committee.
As it is now, in my judgment, we're a little paranoid on technology transfer. And I don't mean that unfairly. I mean, legitimately, we have concerns there. We're all going to have to change our ways at how we do business internationally, and our concern of technology transfer and the protection of our country, which everybody understands. But if we're going to be doing these big things together, we're going to be breaking new ground, we're going to do joint missions to Mars and so with the Soviets and so forth, we're going to have to be in a position of developing new methods, which we don't exist today.
Those concerns held back researchers like Doug Post. He's a Princeton physicist we met last April. That was just before he left for Germany, where he and teams of scientists from around the world are working to design the International Test Engineering Reactor, better known as ITER. The multi-billion-dollar reactor would be a joint project to be built after the turn of the century. Originally, Post and other scientists hoped the Munich conference would actually lead to construction.
But the U.S. Defense Department was concerned that there would be issues associated with technology transfer with the Soviet government. And so they basically downgraded it to a design study.
Before we get to the big construction area, we've got to see this relationship between the Soviet Union and the Western countries continue to mature by quite a bit. I can't tell you how that's going to go. That's up to the Russians.
But if we make proper steps in the arms race control and the disarmament after start and better interrelation, I think why not?
But if East and West grow close enough to start test reactor construction, then where would it be built? Princeton's TFTR is the latest in a series of plasma physics lab experiments. With CIT planned to start in 1996, it's unlikely that Princeton would have time, place, or room for another project. California's Lawrence Livermore Laboratory hopes to build a new laser even bigger than NOVA to perfect inertial confinement fusion. So it's unlikely that ITER would be built there. In fact, it's unlikely that ITER will even be built in the United States. The U.S. is only one of 4 major fusion research nations. The betting money on ITER's location? Somewhere in a rural tract in Europe.
We're very nationalistic when you get right down to it, and I think this, especially in the Congress, you'll see a lot of resistance to having that U.S. money go abroad.
If we had to stop some of our own plasma work in this country that we're working on, again in Princeton and Tokamak and so forth, and versus participating in funding an ITER program in Europe, I think we would work with, I know we would go to the domestic end. You understand where I'm trying to come from? So I don't think that the decision process is at hand as yet, nor do I think that the case is set, and anybody determining that that program would be built in Europe or any place else at this point.
So why don't we start with our usual agenda and see what the status is of the machine, beams, and so forth.
But before ITER, there's still TFTR. Every Monday morning, Rob Goldston leads a crowded conference updating Princeton Tokamak progress.
We had about 3 or 4 choices of problems on the RF limiter, and it turned out the difficulty that we're seeing, the hotspot, most likely was an insulator on the limiter mounts.
It's like managing a baseball team, except here they use computers instead of bats, and their field is a mysterious and challenging level of plasma physics.
We'll have to talk about how we implement this procedure to save the machine and also let us operate.
But if TFTR works, the machine won't be saved. It only burns deuterium now, but in 2 years, Princeton plans to wrap up research with 100 tritium shots. Resulting radiation will make TFTR literally too hot to handle. Maintenance would require special tools and special robots. Those planned tritium shots raised government concern. Federal research found TFTR's radiation would pose no danger even in the unlikely chance that safety systems fail. In fact, a geology study concluded there's only a 1 in a million chance that even harmless trace amounts of tritium would penetrate underground water supplies. Yet tests are underway to see if in a worst-case scenario, like a major fire, nearby Princeton neighbors would still need an emergency response plan.
Leaking radiation apparently went unnoticed for 3 hours yesterday. The nuclear reactor at the 3 Mile Island plant overheated and shut down at 4 a.m.
3 Mile Island, a symbol for what can go wrong with nuclear power. Loose radioactivity contaminated one of the reactor buildings. The device itself radiated with what nuclear scientists call afterheat. Afterheat could affect fusion too. Fusion reactors would produce a safe helium ash that's a lot simpler to dispose, than the radioactive waste from today's nuclear fission power plants. And no matter what happens, the reactor's plasma chamber would contain no more than 4 seconds of fuel at any one time. But fusion also makes neutrons that bombard the chamber's wall. That would make the wall radioactive, and that contamination would also spread to the reactor's supporting structure.
But compared to a fission power plant where the thing has that much energy inside, this thing really hasn't got the energy to not only damage itself, but damage a containment building and end up moving out. It doesn't, you feed the fuel in very slowly into a fusion power plant. You don't keep it there the way you have to in a fission power plant all the time.
That's if engineers build it right. The challenge of material science is to develop metals and compounds that resist radioactivity.
The material of the first wall cannot work in such big neutron fluxes 30 years. It must be changed after some 3 or 4 years, and therefore such a reactor must stop and must be repaired, and the first wall must be changed. That is not a commercial kind of machine.
We might even be able to make a wall that lasts 30 years. And there are other possibilities too. We may go to a fuel cycle that doesn't involve tritium, for example. Then the neutron flux on the wall goes down a lot.
A safe fusion fuel cycle might involve a little travel, like a trip to the moon. The moon is loaded with helium-3, an isotope not found here on Earth. Burning deuterium and lunar helium would be a lot safer than tritium. Both Soviet and American space programs plan some lunar mining missions, possibly to bring back helium-3.
The lunar helium-3 can be energetic and maybe economic, with energetic and economic advantage in comparison with all other fuel existing on the Earth. That is, I think, our goal, to give to the mankind power without radioactivity or with a very low level of radioactivity.
Engineers think a fusion reactor might look something like this. There'd be a concrete igloo to contain radioactivity. Robotics would be needed to maintain the reactor structure. Such a reactor could be up to 50 years away. But the promise of fusion provides fuel for imagination. It could not only power our utilities, it could run our rocket ships too.
On almost every count, fusion would seem to be superior to fission. The only catch is that we don't have it yet.
But Isaac Asimov uses fusion all the time. His noted science background helps him dream of worlds that turn from today's heavy chemical rockets to tomorrow's faster fusion rockets that burn lighter hydrogen fuel, meaning a trip to Mars that would take us months today might only take a few days tomorrow.
We'll be able to pack more energy into a spaceship so that we can have more bang for a buck. What we really need to make my science fiction work is faster than light travel. But I don't consider that much of a possibility at all. Still, with fusion alone, we ought to be able to reach any point in the solar system we want without too much trouble, and maybe, if we take a little trouble, reach some of the nearest stars. I must admit that I had rather thought that we'd have done it some time ago. The fact that we haven't done it yet is a little disheartening.
That disappointment is felt by a growing number of scientists, as well as the very industry that would sell fusion power.
At this point, there's a significant risk in whether or not fusion will actually work.
Ken Mattson works for the New Jersey utility that supplies the energy that runs Princeton's TFTR. Utilities don't supply much more than that to support today's fusion research. Beset by problems plaguing the nuclear fission industry, they're waiting for more promising results in fusion before jumping in.
If you had fusion that worked, but you couldn't maintain it economically, or you couldn't operate it economically, then it isn't a viable technology, even though it works. It's not a viable technology for our ratepayers.
That doesn't mean power companies forget. Nestled beneath California's purple foothills lay sprawling research. Microchip manufacturers, computer firms, laboratories, they checker flatland south of San Francisco, appropriately called the Silicon Valley. Among the science centers here, the Electric Power Research Institute, a think tank supported by the American power industry. They think a lot here about nuclear physics. But Dr. David Whirlidge also thinks about fusion, a much different type than current research.
The technique here is to try to avoid the use of plasmas, or at least to try to avoid the use of very high energy.
It's called muonic catalytic fusion, in which a bulky, heavy electron acts like a powerful glue, bonding deuterium and tritium a lot more tightly than a normal electron would. So tight, the nuclei run a better chance of fusing. And instead of super-hot plasmas, particle accelerators would generate muons at low temperatures. It's an old idea littered with technical problems, but EPRI sees new promise.
We're interested in this process because at a very low level of funding, with very small-scale experiments, one has an opportunity, perhaps, to participate in a breakthrough, perhaps in the next 5 years.
We may need a breakthrough on any type of alternative energy source for more reasons than we realize. Most commercial power plants today not only make energy, they make pollution too. The fossil fuels they burn send gases into the air. And it's not just power plants. Anything that burns also pollutes. They fill our skies with carbon dioxide and nitrogen oxide, along with other man-made pollutants, chlorofluorocarbons and methane, gases that have come to be known as the greenhouse gases. Greenhouses trap sunlight and heat, an efficient way to make plants grow better. It works well for botany, but it's not so good for humanity. As greenhouse gases encircle the Earth, trapped sunlight raises temperatures, making climates change. Professor Ned Reese teaches meteorology at New Jersey's Rutgers University in New Brunswick. He's accustomed to tracking weather patterns like winds, rain, and humidity, but lately he's been tracking something else.
What we're looking at here is the global average concentration of carbon dioxide for the last 23 years, beginning in 1958 and extending up through 1981. And the ups and downs that you see here are the variations over the course of each year. Carbon dioxide increases and decreases with season. But the important thing to see is that the general trend has been upward, and it shows that during those 23 years there's been something like a 10% global, worldwide increase of carbon dioxide that has taken place.
There are signs that the greenhouse effect is taking its toll. Some meteorologists point to recent heat waves and a costly Midwestern drought. There's evidence of desert migration in Africa that's gobbling up the already limited farmland. And if the greenhouse keeps up, scientists fear some melting of the polar ice caps will make the oceans rise, triggering beach erosion and floods.
It's possible that some of the things that have taken place in the Sahara Desert regions, the droughts that we're seeing now, could be some of the first manifestations of that, kind of a forerunner of things to come. But the time range that we're talking about, where the effects are going to become incontrovertible, is going to be in the next few decades. It's going to be very, very difficult to do anything about it because the fossil fuel combustion is something that has been an integral part of our civilization for a very long time. The most important thing that we could do would be to try to go to some alternative types of fuel, but building a few nuclear power plants or nuclear fusion facilities around the U.S., for example, probably wouldn't have too much of an effect. It would have to be a very large-scale type of a thing to really make a difference.
Now, there's speculation in how strong those effects are and how much carbon dioxide it takes to create that sometimes called greenhouse effect. But it's only prudent that we look to other forms of power generation which don't create carbon dioxide for the long run, so that we do manage to maintain our environment in a form that we find both productive, comfortable, and otherwise acceptable.
Presidential science advisor Dr. William Graham works in the old executive office building next to the White House. His office is down the corridor, from the room where Lieutenant Colonel Oliver North and his secretary, Fawn Hall, shredded Iran-Contra documents. But for Dr. Graham, that nearby modern American history is hardly as significant or pressing as what man's doing to Earth.
These aren't short-term effects I'm talking about. Earth's a big place. It's got a big atmosphere. But over the long run, we want to be careful that what we put in the atmosphere doesn't have undesirable side effects. And fusion can help in that.
Our sun has been burning for over 4 billion years. It's only in the last 100 years that we've really come to understand why. Perhaps in the next 100 years, we'll also learn how to harness the sun's energy here on Earth. On paper, fusion energy sounds like a clean, safe, limitless source of power. But to make a son of man here on Earth will take some hard decisions. After 40 years of expensive research, can we afford the cost of 40 more? Can we afford the risk that maybe it won't work? If you ask the scientist, you'll be told, we can't afford to wait.
With a growing human family, we're going to need more energy to power the world, and there just aren't that many sources of energy around. I looked up the population figures the other day, and at the time that the fusion program started, there were 2 billion people in the world, 1953. Today there are 5 billion people in the world. It's it's more than doubled. By the time we find out whether or not we can really build a fusion reactor, say shortly after the turn of the century, there'll probably be another 3 billion people in the world. And by the time we can start producing energy with fusion or any other new technology, we're talking about 10 to 15 billion people in the world. There's just simply no way you can support that population with conventional energy sources.
Fusion, of course, is designed not for us, but for our children's future, because we know that in the 21st century, the world is going to run out of coal and oil. And what are we going to do when that happens? If we don't do the work now, we won't be in a position to ensure our children's energy future and their standard of living in the 21st century.
The time when there will be a lot of fusion power being commercially applied, when fusion takes over a good share of the power requirement, will be sort of 2040, 2050. That seems like a very long time away, but if you draw a little graph on when the crunch really hits, the rising power requirements around the world with the growing population and the rising standards of living, crossing over with the falling fossil fuel resources, you find that the crunch hits in 2050. So that is not a bad time to be able to shoulder a big piece of the load.
Because the fusion mostly depends on our brain, not from the resource and other. In the modern time, high technology win. In such case, I am sure we win. But how fast is the question?
Fusion is so important to the future of the world, to populations, to civilization, that it's a technology that we have to develop. We can't afford to overlook any options.
It will be something that's useful for mankind. Maybe my grandchildren, my own children now are of an age that this won't happen in their lifetime. It's like working on the first layers of a pyramid. You can see the final product in your mind, but it'll be generations after my generation that will actually finish this.
I'm reasonably confident that within a few years we will know that the laws of physics make it possible to extract energy from fusion for the welfare of mankind.
We have no right to have another Chernobyls.
Plasma. What is plasma? That's not part of your blood. That's not what we're talking about. A plasma is a fourth state of matter.
They could be future plasma physicists, but today they're only visitors. Princeton's Plasma Physics Lab runs hundreds of tours each year. This one is no different. As always, the lab's auditorium rings with curiosity and questions.
When this thing's running, what's like the radiation level on the floor?
Very high.
While chasing the fusion mystery, plasma physicists often find themselves splitting time between science and public relations. They know how good PR helps save federal funding, but it also helps educate and inspire. It may take 2 more generations of plasma physics before the world enters the fusion era.
This is the best we've ever seen.
That was the last balance shot that we had, was 795. Is that good enough to try to get a temperature, or is that...
For nearly 4 decades, science has been struggling to make fusion work. There are still decades to go before 2030, when the first fusion reactor may go online. Those future fusion scientists will get their cues from the Rob Goldston generation and its dedication to mastering the atom.
Sometimes down on the shore, when the sun is out and it's very hot and I have my little boy with me, I'll explain to him that the power that's coming out of the sun is one of the sort of fundamental powers that the universe has, and it's that kind of power that we're trying to harness for fusion energy. And I think he gets a kick out of seeing that that's what his dad is working on.